4.5 is about everything that we've been leading up to. It's bringing everything together from an exponential and logarithmic equation standpoint, using these techniques of converting that maybe we learned in 4.4, or expanding or condensing in 4.3 with logarithms, to really take somewhat complicated equations in either exponential or logarithmic form and getting answers. For example, if we had 7 to the x equals 12, this is a basic version, but obviously 12 is not an even power of x. We could take the logarithm of both sides, which would allow us, using our logarithm rules, to bring x in front and then divide by the log of 7, and here we could approximate using a calculator. Now we won't do this one on the front page, it's more complicated than the ones we need, so we'll talk first about exponential equations with base e, and then move into some different logarithm equations over the next video or two. So base e exponential equations. To isolate a variable in an exponential attached to e, you must take the natural log, or the log base e, of both sides. From there you can solve for the variable. Now there are a few rules. We can never take the logarithm or natural log of a negative number. If you get an answer such that you get log of -5 when you plug it back in, that's not a solution. Our general strategy for exponential equations would get all of the e's on one side by themselves, or possibly two sides, and then take the ln. So on number 1, the e's are already by themselves, so we can take the log, or the ln of both sides. The ln of e to the x squared equals the ln of 200. On the left side, this gives us x squared equals the ln of 200. So the ln and the e will cancel, and the x squared would have come out in front before that happens. Okay, and then from here, what we would normally do is take the square root to solve for x. Take the square root of both sides. To get x equals plus or minus the square root of the ln of 200. We may not really know exactly what that value is, but we do know that that is a number, and you can use the calculator to approximate if they ask you for decimal answers, but on the test, you won't have a calculator, and all I would want you to do is just leave it like that. Plus or minus square root the ln of 200. Now, how is this different from number 2? Number 2, there's a whole bunch of e's, so the first thing we need to do is get all the e's together. When I'm multiplying with the same base, I add the exponents, so e and then to the 2x plus 1 plus -4x equals 3e. When I combine those, I get -2x plus 1. Now, technically, all the e's aren't on one side yet. I can divide this by e to move the e over. This is e to the -2x plus 1 divided by e to the -1. We subtract, and the 1's will cancel. So this is e to the -2x equals 3. From here, I can take the ln of both sides. So the ln of e to the -2x equals the ln of 3, which means that -2x equals the ln of 3. And from here, to solve for x, I would divide by -2, or multiply by -1/2. To get that x equals -1/2 the ln of 3, or negative ln of 3 over 2. Either one of those should be fine. Again, since I'm not putting anything inside a logarithm for now, I know it's fine that I'm not going to end up with a negative inside the logarithm. Now, if you recall back to chapter 1 when we had quadratic form and the u substitution, we can now do this with exponential equations as well. How do you know when you're going to have a quadratic form? Your big hint will be that the power of one of your e exponents is exactly twice as big as the other one. So 2x is twice as big as x. And of course, it's this middle term that always ends up being your u. So your u equals e to the x in this case. So this is really u squared minus 4u plus 3 equals 0 when I convert it. So that, when I factor this, I get u minus 3 times u minus 1 equals 0. And of course, the solutions to that are when u minus 3 equals 0 or u minus 1 equals 0 by the zero factor property, or the fact that if two numbers multiply to 0, we know that one of them is 0. So u equals 3 or u equals 1. Now, if the problem didn't start as u, it does not end as u. We know that u is actually e to the x. This is e to the x equals 3 or e to the x equals 1. And the way that I solve this is by either rewriting it in logarithm form or taking the ln of both sides. So x is the ln of 3 or x is the ln of 1. Now we know that the ln of 1 in any logarithm of 1 is 0. So we get x equals the ln of 3 or x equals 0. Here's a situation where we could have the ln or the logarithm of a negative number, so we need to make sure to check and see that this works. Another one of these, 3e to the 2x plus 2e to the x minus 1. Again, we'll let u equal e to the x. This is 3u squared plus 2u minus 1 equals 0. And we factor this. So we're looking for factors of 3 times negative 1, which is negative 3, that add to 2. Well, it shouldn't be that hard. 3 and negative 1. So remember, that breaks up our middle term. So we have 3u squared plus 3u minus u minus 1 equals 0. So we can factor by grouping. These here are 3u, leave u plus 1. These share a minus 1, share a u plus 1, or leave a u plus 1. So when I factor this, I get my 3u minus 1 times u plus 1 equals 0. What I will do is set each of those equal to 0, just like in the last problem. That means 3u equals 1, so u is 1/3. Here we get u equals negative 1. But of the same argument, I do not leave it here. U is actually e to the x equals 1/3, or e to the x equals negative 1. Now, if I'm solving for this, that x is then the ln of 1/3, or x is the ln of negative 1. Now, your homework may not like the ln of a fraction. Remember, if we use our logarithm rules, this is the ln of 1 minus the ln of 3, which is the negative ln of 3 because the ln of 1 is 0. Now, what do we know about the ln of negative 1? We just put a negative inside of a logarithm. This is a bad answer because we can't have a negative inside logarithm. So their only actual answer here is the one that comes from the first equation. And so this is what exponential equations look like. And we may have some word problems that go with them, but that's all for this first video, and we'll look at what interesting logarithm equations we have in the next video.